Hi everyone, welcome to this past paper walkthrough for GCSE Physics Paper 2. This is an AQA paper from 2024. You will need an equation sheet to be able to do it and also a calculator. It does always help if you've done the paper first and you use this to go through your answers. So let's get started. The first question is all about the required practical to do with refraction. So it's a separate science only practical, but for the first question, we need to know what this word resolution means. So resolution of a protractor is basically the smallest interval between the numbers, or you could say the smallest non-zero reading that it can measure. So if you looked up here, it goes up 10 little intervals between 180 and 170 or 0 and 10. Therefore, the resolution is 1 degree for this protractor and also for most protractors. Then in this paper, we dive straight into the 6-mark method, all about this practical on refraction. We've got some results here showing how the angle of incidence changes and how the angle of refraction varies as a result. And we've got to describe a method, quite a standard question, this one. We do have a chance to include a diagram, which I would always recommend because it usually, as long as it contradicts your writing, it can't really harm your writing. So I'm going to show you how to do a proper method. Don't forget we can use bullet points. We should use bullet points, and step by step we should also make sure to mention all the equipment we can. So I'm going to draw the diagram first, just so I can explain, hopefully remind you guys about the practical itself. When we're drawing a practical, we don't need to draw the ray box in or anything like that, or a table or paper or things like that. We just need to draw the block and label the angles, where the ray goes in, where the ray comes out. So in essence, what we do is we have the ray of light coming in. However, we've got to draw on what's called a normal. So normal is at 90 degrees to the surface that it's entering at. And when we measure the angles, so it doesn't really matter what angle this one is here because it's just a diagram, then we measure the angle of incidence is the angle between the ray and the normal. That's why we draw a normal on, so we can measure this angle here. The angle of refraction is not down the bottom, it's actually this one here, and it'll get a bit closer to normal when it enters glass, and the angle will be this bit here. So I'm just going to label it to the side so it's nice and clear. That's my angle of refraction. So even if it's not clear from my writing, I'll still get marks because the examiner knows that's what I mean when we talk about those angles. So let's go through the stage by stage method of what you could write then. So first one I'm going to write up here because I'm going to write probably more than you need for 6 marks, just because I could write down all the different things you could say. First step is to place the block, the glass block, on a piece of paper. Now the idea is that you have to be able to draw around it, which we'll mention in a second, so it therefore needs to be on paper for you to do that. So then we're going to draw around the glass block, as I've just mentioned. Then, just as I've drawn up here, there's a ray box up here. You don't, like I say, you don't have to draw it on, but we're going to shine or use a ray box to shine a beam of light into the block. Now this is the bit where I might need to add to my diagram a little bit, because we can't do this angle thing yet unless we've talked about how to actually plot where the beam is. Because if you can sort of picture, if I've got the block on the piece of paper, I can't draw these lines in yet. So what you're going to have to do first of all is you shine your ray of light in. We're going to talk about the angle, then we're going to talk about where the ray comes out, basically. Okay, so what we're going to do is draw a normal at 90 degrees to the block surface, or you could say perpendicular to the block surface, and then you're going to basically mark the ray entering and leaving the block. Now, when we say leaving, what I mean is this. So we can't mark it in the center. However, when it continues through the center of the block, and like I say, you don't need to draw this in your diagram, but just to make it a bit clear what you mean, the ray of light will come out here. So you mark on with some X's, and then you basically replace the, take off the block, and then you'd sort of join these up so it's obvious where the ray of light goes. Then you can join this bit up in the middle, basically. So we're going to say, join the line up from entering, when it enters and where it leaves the block. And next is the measurements. So we've drawn it on our diagram already, so you actually don't need to say in this next bit where the angles we're measuring are. We do need to say use a protractor. There's also a giant picture of a protractor there. Don't lose marks for not writing that in your answer. So use a protractor to measure the angle of incidence as it says in the table down here, and the angle of refraction. If you didn't manage to put in your diagram, you'd have to say something like the angle of incidence between the beam and normal, and the angle of refraction between this beam or this ray of light and the normal. It's just so much easier to draw, so I'd always recommend drawing it if you can. So next, what we're going to do, we're talking about this table here. That's what the question asks us, how do we get this data in table 1? So what we're going to do is basically vary the angle of incidence, and we haven't actually mentioned any numbers where we start from yet, but we're going to say, so start from 10 degrees, that's the lowest it starts from, and then increase by 10 degrees each time until 60, because that's the last set of results we've got on our table. So once we've then done that, basically we don't need to talk anything more about errors and inaccuracies, things like that, because it's just mentioned to plot out the 6 mark method. You could say things like use a nice thin beam, don't jog the table where the block is, things like that, but that's absolutely fine. These results, that's the method how we do it, so that's absolutely no problem. 6 marks. To follow up to the 6 mark question, we've got a graph, we've got 2 points to plot on. We've got the angle of incidence of 70 and 80, so this should be the easiest marks on your paper, so just make sure you're doing it carefully. 70 goes up to 35, do an X just like the rest of the points, don't do a circle, and then 80 up to 37. And once we've done those, it said we should plot the results, done that already, and then draw a line of best fit. Now, some people get confused with these, okay? Lines of best fit don't have to use a ruler, they don't have to be straight. And this bit looks a bit straight, but hopefully you can see after about 40-50 degrees it does start to curve. So our line of best fit here should be a curve. It can be a curve, it doesn't have to be, but if it looks like a curve, like this one does, if you put a ruler next to it, then it probably is a curve. So we're going to draw something like this, and my tip is use pencil. I'm not going to because it won't show up as well, but do it going away from you. You can't do like hairy lines like this, you can't do a sketch, and just make sure it's one line, do it in pencil, so if you go wrong, you can always rub it out and go again. It doesn't have to hit every point, same as a straight line of best fit, but something like that would be absolutely fine. And this also shows how the next question, how do we know they're not directly proportional to each other? Well, if they were directly proportional, we should know that as one increases, the other increases at the same rate. So it's a straight line through the origin. So simple enough here, you can say the line curves or the line is not straight, is absolutely fine for the mark here. Got some more drawing to do for question 1, which again you should use a pencil for. I'm not going to because it won't show up. This time we've got some reflection. We have been told that this surface is a reflective surface, so we're going to have to draw in the ray diagram to show the reflected ray of light. We've got to also draw a normal line, so don't miss out this question here, even though it's right down the edge of the paper. Should be a nice easy 2 marks. If we draw a normal line, so normal line should be 90 degrees to the surface. Obviously get a protractor out, do it properly, but that one you could definitely just do by eye. And the next bit you would definitely will need a protractor for. Again, I'm not going to here just to save a bit of time, but the angle of incidence, so this ray here, should equal the angle of refraction, so this ray here. So the angle it comes out at should be pretty much the angle it comes in at. They will judge it by eye, but do it properly in the real thing. So something like that will be absolutely fine for your 2 marks for that question. Next, the ray of light goes to a transparent cover of a headlight. Transparent means the light. Transparent means the light goes through it, but it's going to refract. So which ray of light sort of looks most reasonable? It's definitely not going to do this because that's reflecting. If you look at this one up at the top here, it gets a bit closer to normal, and then it goes a bit further away at the same angle it came in at. So it is going to be the top diagram for 1.6. Let's move on to question 2. Let's move on to question 2, which is all about forces and resultant forces first of all. So the child is standing still. What is the resultant vertical force on the child? Now, we don't have any information on the diagram. Usually in that case, there's no information. The answer is either 0 or it's somewhere else in the question. We can also just figure out, because the person's standing still, that means the resultant force is going to be 0 newtons. Now, the reason why is, like I just said, kind of relatively straightforwardly. There's no information given to us about the forces, but we do know that all the forces must be sort of balanced, or the up must equal down, left must equal right. You could also say the child isn't accelerating. That would be fine. So I'll say just something like the forces are balanced, or they're not accelerating, and that'll be perfect for that second mark. Next, we've got an equation question, the first one on the paper, easy peasy mark with the equation sheet, work done equals force times distance. Next, we've got to actually apply them to this question. We've got a distance of 2.8 meters, we've got work done of 35 joules, we've got to work out the force. So with all questions involving equations, I like to use the method FIFA or something similar. Do not use triangles, don't try and rearrange, because if you go wrong, you're going to get no marks at all. The way FIFA works is F for formula, so I'm going to write down the formula again just so I can keep track of my numbers. And then I, it's the most important step, is to insert values. So this is the first mark for AQA and other examples as well. Work done is 35 joules. F I don't know, so I can write out the letter F, or I could write down X or a question mark. Distance is 2.8, and before you get a calculator out, you've nailed that first mark just in case you mess up later. The next step is for fine tuning, so I've got to find out what F is. Now I've currently got F times by 2.8, so if I divide both sides by 2.8, it's going to cancel from here, and it just goes over to this side here. So divide by 2.8 gives me, if I had to put that into my calculator, is 12.5 newtons, which I'm going to write on my answer line, and that's my 3 marks there. The child then pushes the baby walker from a carpet to a hard floor, and it says they apply the same horizontal force. Why is the speed going to increase? Hopefully we know, you might have done a practical like this in school, different surfaces have different amounts of friction on them. So we could say something like, and there is less friction on the hard floor, or we say there's more friction on the carpet. And then the second mark's a bit harder to get here. That should be an obvious one, that first one. So that means there's less friction, so therefore there's going to be more resultant force applied to the walker. So if you imagine the walker, let's go to the diagram from earlier, it's going forward, and there's a little less friction than there was before, therefore there's going to be a bigger resultant force going forward, or in the forwards direction, provided by the walker moving along. Next, we've got a question all about moments and gears. This is for separate science students only. First of all, we've got a question or equation we need for moments. So moment equals force times distance. Again, straightforward, easy mark. Everyone in the country is getting that. Next, we've got to work out the moment. So moment equals force times distance. I'm going to use my FIFA method again just to keep track of all the stages. So we're going to insert values. There's actually not loads to do here other than we need to spot that this is not in meters, it should be in centimeters. So therefore we need to convert it. So I've got moment equals 2.0 times by, and centimeters to meters, you're going to need to divide by 100 because there are 100 centimeters in every meter. So that's then going to be, put in your calculator, don't just guess it, that's going to be 0.075. Is going to be the distance it travels, and you just put those into your calculator. We can kind of skip out this stage really because we don't need it here. Is 0.15 meters, which is here. If you didn't do this conversion, if you got 15, then you would have got 2 out of 3 marks as long as your working is clear, but that's what you need to get for full marks. Next, what happens when the child applies a force to force A? So so gear A is going in this direction. So if you imagine gear A turns around here, we're going to figure out what happens to gear B. So imagine the teeth are going this direction. This is currently going anti-clockwise. So therefore B, if you kind of imagine this moving, it's going to go in the opposite direction. This is going to go in the clockwise direction. And we've got to be able to explain that as well. So let's have a look at what an answer would look like. So gear B, we just say gear B rotates, you could say in the opposite direction, but you could say clockwise, which is a bit better. So that means it goes sort of 12, 1, 2 in that direction. And the reason that happens it says because gear A exerts a force, or you could say exerts a moment on gear B, which I know seems like an obvious point. Sometimes answers are obvious because it's touching it, it exerts a force this way round. So therefore this exerts a force here. So therefore this moves this direction. So that's all we need to say for our 2 marks. Question 3 is all about space and the space topic. So this is for separate science students only. And we've got to name, first of all, 3 other types of object that form our solar system other than our sun. Now, we've got lots of different choices here. The easiest one is to say planets. Obviously, there's 8 planets. Plus, there's dwarf planets. So you could say Pluto is a dwarf planet. It's not an official regular planet anymore. Sad times. You could say things like moons. You could say satellites. Like any of those would be absolutely fine. You could say asteroids, meteors, comets, also for that question. Next one down is a bit of a sort of comprehension task. So we've got 4 different stars here, which will eventually form black holes. We should know that this only happens to high mass stars. So we've got to look at which ones has the highest mass and figure out which one's most likely to form a high mass star. So let's look at all the standard form. There should be obvious. There's only one that is a bit heavier than the others. That would have an extra 0 on the end. That's what the standard form notation means there. So therefore it is going to be this star called Betelgeuse, which, fun fact, it could go supernova tomorrow. It could also take 100,000 years, but it would be like a sort of moon in the daytime, basically, in the night sky for a few weeks if that were to happen. The next one is looking at prefixes, so gigameters. Giga is one of these prefixes you need to know, like, for example, kilo, mega, giga. We need to know what values they are because they're often used in physics exams. They're useful in real life. Giga is 10 to the power 9, or it's a billion meters. So 1.1 times 10 to the 8 gigameters. We just times together in a calculator. 1.1 times 10 to the 8. And then you just either do it in your head, but just do it in a calculator just to be sure, times by 10 to the power 9. And that comes out as this option here, 1.1 times 10 to the 17 meters. Next, we've got a question all about redshift. So we've got some light spectra from different galaxies, and it says the lines have the same pattern. So the lines you see, they're all in the same form, but they've shifted to the right or a bit to the left. It says, explain what these light spectra tell us about the velocities of galaxy A and galaxy B. Now, it doesn't say speed here because it says velocity, because direction is important. So there's some obvious points we could say here. This is the sun. So our sun is stationary. It's not moving relative to us. Obviously, we'd be in big trouble if that was happening. If we compare that to different galaxies, we see these lines that we get from our these galaxies are shifted towards the red end of the spectrum, blue here and red here. So because that's happened, well, let's write down that mark first because that's quite nice. So both galaxy A and B show redshift. They move towards the red end of the spectrum. What that means is that they're moving further away from us, or they're both moving away from the Earth or moving away from us. Now, we might notice they've redshifted by different amounts. So galaxy A has a greater redshift. So what that means, while they're both moving away, is that galaxy A has a greater redshift. So actually, it's moving faster than B. So it's moving at greater speed or moving faster than galaxy B. And that's enough there. That's our first mark. That's our second mark for identifying that. Our third mark for explaining what that means. So there's some obvious marks here, and you've got to be able to differentiate between those two lines there to be able to get your full 3 marks. Next, we've got a calculation question, which the only thing difficult about this is that we've got some sort of tricky standard form to use, but make sure in your calculator using brackets would be my top tip. We've got speed, we've got distance, and we're trying to work out time. So the equation you'll learn from maths, speed equals distance times time. I'm going to use the other version, so distance equals velocity times time, because that's the one on your physics equation sheet, which obviously you get in the exam, so make sure you know how to use it. So distance, I'm going to write out the whole thing, even though it's going to be a bit long because it's in standard form. We're going to write down there. Speed is 3 times 10 to the power 8. And I'm going to put brackets around both of those, so I remember to do that in the real thing. And then time, we don't know. So our fine-tuning stage is going to be, how do I get time by itself? It's currently times by 3 times 10 to the power 8. So I've got to divide both sides by this, just like we did earlier in the paper. So again, brackets round, just in case we lose track of our numbers later. And that's how you type it. So on your calculator, make sure you can do brackets. So for example, for me, it would be 3.6 times 10 to the 14 divided by 3 times 10 to the 8. And if you do all that, you're going to get a value for the time taken of, what was it, 1,200,000. And we don't need to put it in standard form. You can do, but it's the same thing, 10 to the power 9. And even though it seems really big, don't forget we're talking about space here, so big numbers are quite standard. Next one's all about star formation. So when stars are formed, they contain mostly hydrogen. Describe how stars produce all other naturally occurring elements. So basically everything apart from hydrogen. So it's a 4-mark question. Let's do some bullet points and let's think about star life cycles and how we can use that information to help answer this question. So inside our sun, we have, this is the main sequence star. Inside the main sequence, we have hydrogen being fused together with other hydrogen nuclei to form helium. That's another element, so we can talk about that here. Next, we're going to talk about after a star runs out of hydrogen fuel, it turns into a red giant or a red supergiant. Now, depending on which one this is, it can form heavier elements, but either one, we're going to have heavier elements formed there, and this is up to iron, And then after that point, we then, with a red supergiant, we have a supernova stage, which is the really heavy elements. So that's kind of like draft answer. So let's then talk about the helium to hydrogen to helium first of all. So we could say nuclear fusion in a main sequence stage means at high temperatures hydrogen nuclei form helium nuclei or join to form helium nuclei. Now, some of you might know it's not quite as simple as that, but for GCSE, that is absolutely fine. I missed out the important word there, helium nuclei. So that's absolutely perfect for a mark or two in this question. However, like I said, once the hydrogen runs out, so hydrogen runs out, then we're going to have heavier elements fuse together, or fuse, and that's, like I said earlier, up to iron. And then in very or high mass stars, so not all stars, but high mass stars, they're very heavy elements are formed in supernova. Now, when we talk about very heavy elements, we are talking about, so these ones here, e.g. like uranium, gold, silver, stuff like that. So on a periodic table, really heavy ones, you do need to know, even though you don't get a periodic table, you do need to know that those are the heavier ones that we would find if formed in these supernovae. Let's move on to this next question. This is all about pressure in water. We've got a submarine that's going deep down to the Mariana Trench, the most deepest part of the Earth's surface. And it says, as the depth of the submarine increases, explain what happens to the pressure on the submarine. So it doesn't actually say what happens to it, whether it goes up or down. So that's an easy mark, is for saying, well, what happens to the pressure? However, unusually in this question, we actually don't get a mark for just for saying that pressure goes up. We've got to say sort of why that happens. So the idea is the deeper it goes, so let's say it's now at the bottom down here, there is a higher amount of water above it. So therefore there's a higher sort of mass of water above it. So you'd say something like deeper it goes, the larger mass of water above the submarine, or is above the submarine. We can put a sub there to save a bit of time. And then later, we can then say, well, mass has nothing to do with pressure. We should know that pressure overall is equal to force per unit area. So that's from your equation sheet. If you've got a higher mass, you're going to have a higher force. The force here, in this case, would be the weight of the water above it. So we'd say something like, therefore, there's a greater weight or force above it. So therefore, pressure is going to be increased. You could also say a couple of other equations here. You could use the equation, this one here, if you wanted to, and then say, well, actually, if we've got rho, so that's density and gravitational field strength are constant, then P is proportional to H. But I think that's a fuller explanation. I actually prefer that answer quite a lot. Next, we've got a calculation question involving this exact equation. So as you saw, our equation sheet, and it's the only one that's got pressure. There are only two that have got pressure in it, which are, where they've gone this one down here. This is pressure in a fluid. So let's write that out first. So pressure is equal to, and we've got height times by density, don't forget it's a curly P or a rho symbol, times by gravitational field strength. We're trying to work out the depth. So depth is basically height in this question, even though it sounds like it's a similar thing. A different thing is basically the same thing. So let's again use FIFA to work out what we're talking about, work out the depth. So pressure we've got, this first of all, that should ring alarm bells, that's K for kilo. So that means times by 1,000 or 10 to the power 3. So therefore that means, even though it makes the number a lot bigger, that's okay because it's a lot of water underneath it, so a very high change in pressure. That means instead of being 110,000, it's actually 110 million. So that's our pressure value. So we're going to write that on this side first, or you could do it in standard form if you wanted to. H, height, I don't know. Density, I do know. That's given up here as 1026. And we've got gravitational field strength over here is 9.8. That's our 1 mark for that, 1 mark for doing this as well. I would then do, you don't have to do this bit, but just to make life a bit simpler, is to just times these two numbers together, just to make it look a bit easier what to do next. So times in 1026 by 9.8, which is 10054.8. And then the left-hand side stays the same. We've not done anything to this side at all yet. Next, what we're going to do for our fine-tuning section is how to figure out how to get h by itself. We need to get rid of this times by. How to get rid of a times by something? Well, we divide it on this side so it cancels, and we have to do the same thing to both sides because we're good mathematicians. So therefore, it's going to be 110 million divided by, this is a big old equation, isn't it? That figure there, which if we put that all in, we should find h is going to be equal to 10,940 meters. Or we could round it to 11,000 if you wanted to. Big number, don't forget this is the deepest part of the Earth's surface, so 11 kilometers sounds a lot, but it's actually not too crazy. Okay, next question we've got is all about seismic waves. So we've got earthquakes occurring in the Mariana Trench, P waves and S waves are produced. We've got to describe P waves and S waves to figure out which one is correct. P waves and S waves are longitudinal, that's not correct. P waves and S waves are transverse, not correct. P waves are longitudinal, S waves are transverse. The way to remember it is that in the word transverse you have an S, so therefore S waves are transverse. That's not why they're transverse, it just helps you remember it. Now when these earthquakes are produced, they go through the center of the Earth and they go sort of from one side of the Earth to another. However, we can have a look at what happens to P waves and S waves and figure out, it says, which letter do we only have P waves being detected, so basically no S waves. So if we have the earthquake here, P waves can go through, we've got solid and liquid, P waves can go through all of it. However, S waves can only get as far as here because they cannot get through liquid. So actually when we think about part D, we are not going to have any S waves being detected and they cannot travel through liquids. So we say something like S waves cannot travel through liquids. And that's pretty much the only facts you really need to know about S and P waves, is that P waves are longitudinal, S waves are transverse, and S waves cannot travel through liquids. So they can all get to here, but S waves cannot travel through the center because there's liquid there. Next up, we've got another calculation question. Should be a relatively easy 3 marks, although we have got conversion to do straight up. We're trying to work out the wavelength. We've got frequency and we've got speed. So our formula here is going to be velocity or speed equals frequency times by wavelength from your equation sheet. We're going to insert our values. As I mentioned, this is kilometers per second, so this needs to be in meters per second. That's the standard unit for speed, so therefore that's 4,500 meters per second. So that's going to go in our velocity. Frequency, we also know is 3.6. Wavelength, we don't know, so I'm going to leave that as the symbol. We could write an X or something like that. To fine tune it, we've got to get rid of the times by 3.6. We can divide both sides by 3.6 and see what that gets us for a final answer for our wavelength, which is 1250, which is quite big for a wavelength. However, it's not too crazy. That's not too big, I wouldn't say. Now, the next question, you've just got to read the question and you've got to be really specific with which relationship you're describing. So ignoring the rest of the information in the question first, this says describe the relationship between the distance from the earthquake to the seismometer and the time between the P wave and the S wave arriving. Those are the only two things you need to talk about. This question does not ask for any extra information about the velocities of each two. It tells you in the question that's what you should be coming up with. Now, if we know that P wave travels at a known speed, S waves travel slower, that's why they're called S waves. They arrive later because they're secondary waves, but they arrive at different times. They do not need to have any more information about that. All you need to describe is how the distance affects the time between them arriving. So basically, if they're further away on the Earth, so let's say further distance, so here compared to here, there's going to be a greater time for the waves to, or greater difference between the P waves arriving and the S waves arriving. The reason for that is because of this equation here. So basically, if they're we'll talk about the speed and the distance. So there's a known speed between an earthquake, P waves are a known speed between an earthquake and a seismometer. We know S waves travel further. So the idea is that the distance is going to be, basically if distance is increased, that means the time taken between them is also going to be increased. They are directly proportional. So you get a mark for saying one goes up, the other goes up, but the true definition is that the distance, and I know it's going to be a pain, but just write out the whole thing. Don't lose marks for not writing out the whole thing. So distance from the earthquake to seismometer is directly proportional to the time taken or the time between P and S waves. So like I said, that's 2 marks in just one sentence. If you talked about the greater distance means greater time, positive correlation, that's going to be 1 mark, but this is what you'd say for 2. Okay, next in this paper, we've got another question about a required practical. This is the acceleration practical, usually with a trolley or a car and something accelerating it and measuring the acceleration, usually varying the force, but could also be the mass. First one is, what's the name of this force here? Very unknown force generally. A lot of students aren't too clear about what this is. This force is tension. The next question, which is the variable that should be controlled, is the mass. Now, it does allow the mass of the hanger or the trolley itself. Actually, the correct answer is the mass of the trolley plus the hanger. So it depends on which version of this practical you did. However, if you add masses to this, you should technically take them off the trolley. Otherwise, you're varying the mass of the system, which you don't want to do. But if you did say mass or trolley or mass of hanger, they decided that was worth it for a mark in this question as well. Next, we'll talk about how you could measure or describe how the acceleration of the trolley can be calculated. There are loads of different ways of doing that. However, in this question, they want us to use this specific thing. It says the student recorded the time taken for the trolley to travel a measured distance. How can they calculate the acceleration using the time taken and the distance traveled? So time taken and distance traveled, there's a bunch of different equations for acceleration. There's change in velocity over time. There's the v squared minus u squared equals 2as1. And we've also got speed, distance equals speed times time. Now let me explain this one. This one's really, really poorly answered by students. I think it's like under 5%, got anywhere near 3 marks basically. So what we do first of all is we find the distance travelled. We can use that to find the velocity. So we'd say first of all, we have to write it. It doesn't say calculate anything. So essentially divide distance by time to give the velocity, or the speed in this case, doesn't really matter because it's going in the same direction. Next, what we're going to do is figure out, well, I can't just use that in the acceleration one. Acceleration is change in velocity. This is going to be the average. So to work out the change, if you can imagine, it might be helpful to think of this as like a velocity time graph. So velocity time graph is starting off at 0, it's getting higher. The average, so speed, distance, time, would just be basically sort of halfway up. Its average speed, let's say it gets to 10, it starts at 0, its average would be 5. For the change in velocity, we want the whole thing. So what we have to do is to double that average to get to the maximum velocity. So we'd say double the mean velocity. So that's what we worked out earlier. That velocity there is a mean velocity to give the maximum, maximum velocity. Now, in my numbers from earlier, that then makes it 10, which is the total change. So therefore, the last bit is straightforward. We can just use this equation here. So divide the maximum, the change in velocity, which is 0 to whatever that value is, velocity by the time. So we're going to use sort of, not this equation here, but both these equations. We've got to keep an eye on the fact that the velocity there we've worked out is an average. It's not the total change in velocity. You have to double it to find out what that is. There are a couple of ways of doing it as well with this equation, but I think that's by far the most straightforward, and that's the one mentioned first on the mark scheme, so we're going to stick with that one. Next is calculating this thing called uncertainty, which comes up a lot, and students still aren't very clear on how to do it. Once you learn how to do it, it's really straightforward. It's one of the easiest calculations you can do, but you've got to know how to do it. What we do for uncertainty is we find the range of values, and then we divide by 2. So the range of values here, we go from 1.39 to 1.33. So the uncertainty is going to be equal to the range, so 0.06 divided by 2, which is going to give us 0.03, which is absolutely fine for the 2 marks there. Next one is one of the worst answer questions I've ever seen. I think the mark scheme is pretty horrible for this. It's genuinely 0.3% answered on the examiner's report. But I'll tell you how to answer anyway, because it's worth knowing, especially if you're going for those highest grades. This question says the runway was raised at one end. Then it tells us that the force acting through the string remained the same. How does the acceleration when affected by raising the end of the runway? A lot of people figured out it goes up. However, we've got to be careful how we describe how that happens. So comparing the situation to earlier when it was traveling horizontally, the weight of the trolley is acting perpendicular the way it moves, at right angles to the way it moves, so therefore doesn't affect it. Now, however, the weight, because it's at an angle, the weight of the trolley still goes down, but actually there has a small amount of its, the component of it will be acting in the direction the thing moves in, because it's still going to be acting downwards, but the trolley's slope is now at a slight angle. So we'd say something like the component of the trolley. And when we say component, we mean just resolving something into vertical components, basically, vertical and horizontal. So for example, this weight, I could resolve one this way, one that way. So there will be a small amount of it in the direction of travel. So that means a component of its weight is acting in the direction or parallel to the slope or to the runway. And the second mark is relatively straightforward. We'd therefore say, now that means because weight is a force, that means resultant force increases, so acceleration increases. I told you it was hard, right? It's kind of an A-level physics question, honestly, but it is in your specification. You do know about components, you need to know how to draw them and how to describe them, so it is in the spec, so that might be the kind of thing which you really need to focus on being thorough with if you want those grade 9s. The other mark you could get here is by talking about how there's a greater gravitational potential energy getting converted to kinetic energy, which then increases the velocity, so acceleration increases. That's only one mark, and that might be a sympathy mark you get. However, this is the official one given by the mark scheme. Moving on to question 6 in this paper, which we move on to the waves topic. We've got radio waves and gamma rays transfer energy to give 3 other similarities. There's some easy ones here, there's some harder ones. So we could say they are part of the electromagnetic spectrum, or they are EM electromagnetic waves. Then we could say, because they are both EM waves, they travel at the same speed. So all parts of the electromagnetic spectrum travel at 300 million meters per second. You can just say the same speed. You could also say other facts about EM waves, they're all transverse. They are transverse. You could say they can travel through a vacuum, things like that, through a vacuum. That should be nice marks there if you can get them. Next, we've got medical use of gamma rays. They're both used in medicine. Gamma rays are either used for, we could say, medical treatment. So that's like PET scans, medical tracers, anything to do with that is fine, apart from X-rays, apart from MRI scanners. Oh, sorry, that's imaging, beg your pardon, right? So that's medical imaging or medical treatment. Okay, so imaging would be the one that's like PET scanners, tracers, things like that. You could say for medical treatment, you could say radiotherapy. There's lots of different types of radiotherapy that involve gamma rays, but radiotherapy would be absolutely fine there. Or you could put sterilizing equipment, which is another use as well. Sterilizing medical equipment, which means getting all the bacteria off it after procedures. How can exposure to gamma rays be harmful, but exposure to radio waves being not harmful? So we talked about similarities earlier. Next, we're going to talk about differences. So they're both at the other ends of the electromagnetic spectrum. We should know radio is at this end with a really long wavelength and low frequency. Gamma rays have a really short wavelength and a really high frequency. Because of this, gamma rays are ionizing. So gamma and X-rays and UV rays. Gamma rays are ionizing, but radio waves are not. And you have to mention that second bit for this mark. You can't just say gamma rays are ionizing and ask you to compare them both, so you have to say radio waves are not. So therefore you could say, so gamma rays, or gamma, can cause cancer, or they can mutate genes, cancers, or you could say mutate in DNA, that kind of thing, or risk of cancers. That'd be absolutely fine. Radio waves being produced, this comes up all the time in combined science, separate science. They love asking about it. Don't really know why, but they do. How are they produced? Well, in the transmitter that transmit radio waves, they have electrons. The electrons move up and down, and they are therefore oscillating or alternating currents, and they produce radio waves at the same frequency. So we'd say they're produced by oscillations, or we could say vibrations in electrical circuits caused by those electrons. And the idea is they produce radio waves. Don't forget we talked about their frequency earlier, usually quite a low frequency. but they're at the same frequency as the oscillations, basically. So go up and down, let's say 1,000 times a second, therefore it's the same frequency coming out the other side. Okay, next question is all about motion. So we've got a graph on the page here, a velocity time graph. We're trying to work out the distance traveled by the train as it moves along on the first 600 seconds of its journey. So first of all, let's just circle that there. We don't need to worry about anything to the right of 600. We are just concerned with everything up to 600 seconds. The distance from a velocity time graph means to work out the area underneath the graph. So the first 600 seconds, we're talking about the area here. Now, as you might be able to see, it is a trapezium, or it's a triangle and a rectangle together. So obviously use a ruler to do it properly. But essentially, if you work out the area of that triangle, the area of this rectangle, then you'll be able to find out the total distance traveled. So the distance traveled here, the area of the triangle, make it really obvious what you're doing, just so you get your marks, is half for the triangle bit. So let's just call this area A. This is going to be a half times by the base, which is 200 seconds, and the height is, that goes up to 56 seconds. Let's then work that out. So put it on a calculator. That then equals 6160 meters. And let's say area B, the rectangle, that's even easier. That's the area we're working out in the middle. So that's just going to be base times height. So careful, it doesn't go 0 to 600. It goes from 200 to, I've just realized that's not 200, that's 220, my bad. So 220 for the previous one. Sorry, that's the answer, should give 6160. For the rectangle here, we're not going to do a half just because rectangle goes from 220 to 600. So that means that's 380 times by, the height is the same, 56. And therefore that's 21280 meters. So the total, we just add them together. So total area is equal to 6160 plus 21280. And the total distance there is 27440. There isn't a range of values for this because it's on the line and there's no curves or anything like that. So you've just got to look carefully, draw a line from there to there if you think you'll miss it. But that is 56. And don't make a mistake I did, that's 220, not 200. Next is an explain question. Explain what happens to the braking force as the train decelerates. So we should know that F equals ma, Newton's second law, that as the train decelerates, that's negative acceleration. So this is going down, therefore we should know the force is going to be smaller. However, he's got to be using the information from the graph, which is figure 12. So as the train's decelerating, that means it's talking about this whole section here. So not just this bit, not just this bit, it's decelerating for this bit and it's decelerating for this bit. So even though acceleration goes down, resultant force goes down, we've got to say why that's the case. So the idea is that initially, or you could say between 600 and, what is that, about 720 seconds, the gradient decreases. So we can say the gradient decreases, or gradient is less after, and I think you do need to mention for the mark here, yeah you do, 720 seconds. So therefore that means deceleration is smaller, and therefore you need to know the braking force is smaller as well. And just for those who aren't sure, I know it's a bit of a tricky one, because it's steeper, we actually say that's a higher gradient. Even though it's going down, it'll have a higher but more negative gradient, and this will have a shallower gradient or a lower value gradient, even though technically it'll be closer to 0, because we're talking about deceleration here. The maximum deceleration of the train, we are then going to need to get our calculators out again. Now deceleration, which bit is it going to be? Either this bit or this bit. I just talked about this bit being a bit steeper, so let's work it out for this one here. So working out the gradient of the graph, we can see, and I've slightly messed up with my lines here, but this is still 56. It goes down to, this one's a bit easier, it goes down to 20. So that's my first line here, which is 56 over 20. And it goes along, starts at 600, and then it goes up to, this is 720. So it goes down 56 to 20 along from 600 to 720. So therefore the deceleration, we were going to do, it's the same equation as acceleration, it's change in velocity over time. So the y-axis was 56 minus 20. Be really clear on your graph what you're doing and in calculations. So if you miss out by 1, it doesn't make any more difference than just getting 1 mark less. So if I put all those in, I'll get an acceleration of 0.3. Obviously, it's an acceleration of minus 0.3, but the question says find the deceleration, so it's actually fine. You wouldn't get marked down if you put a negative sign here anyway. It does mention that in the mark scheme. Next up in question 7, we've got a multi-step equation. So multi-step equation, we know it's multi-step, meaning it's going to have two different calculations involved, two different equations involved. We know it because it's 6 marks. There's no marks for units or standard form. There's not any conversions here. So let's have a look at what we've got. If you're doing high tier paper, you need to be really good at doing these. So it travels at initial speed of 60 meters per second. There's a force on it of 270,000 newtons. There's a mass given to us. And we also get given the information that it stops. So it starts at 60, so we're going to call that U, and it stops at 0. Obviously, what stops, that means 0 velocity. So it's the final velocity, V, is equal to 0. We're trying to work out the distance travelled. So there should be one thing that jumps out. Even if you can't work out the distance travelled, we can write down some equations, but there should be some that jump out more than others. So some equations we might be asked to use, so F equals ma. We could think about acceleration is change in velocity over time. We could think of distance equals speed times time. We could think of the really nice v squared u squared equals 2as. And then just pick which one of these we can actually use. Now, if we just look at this first one, even though it doesn't help us find the distance, I've got force and I've got mass, so I can find acceleration. It doesn't get you full marks, but it will get you 3 of them. So even if you struggle with these types of questions, work out something you know straight away to save yourself getting 0 marks. So let's just work out our acceleration first of all. So formula is F equals m times a. Our force is 270,000. The mass is 240,000 kilograms. To find out what a is, we've got to get rid of the times by 240,000 kilograms. So I'm going to divide these two, and that's going to give me acceleration of 1.125. Now, technically it's deceleration, so it should be negative. However, at the same time, this also should be negative. So, you know, it was going to sort of cancel out later on anyway, so it doesn't matter too much. So that means we've got 3 marks already just for doing that, which is quite nice. So now we know what acceleration is. We don't know what time is, so we can't use this equation here. It doesn't have distance in it. Only these two have distance. So we don't have time. We do have acceleration. We do have initial speed and final speed, so we can use this equation here we're going to use. So our second round here, I'm going to write down FIFA again, just to keep track of my numbers, is v squared minus u squared equals 2as. And just bearing in mind that if you forget what v and u mean, it is in your equation sheet. V is final velocity, u is initial velocity. So our final velocity up here we said is 0, so I'm going to write down v is 0, u is 60 squared. The acceleration we just worked out is 1.125, and I'm actually going to write x here because my s's look a lot like 5s. I don't want to confuse people. So the s, the distance we're trying to look for, I'll put a missing variable there. So next we're going to do is have, so minus 60 squared, if you put that into your calculator, is 3,600. Now this is where the negative comes into play. This one should technically be negative, but like I said, it doesn't matter because they're going to cancel out on both sides. So we're going to have equals, and 2 times this is going to be equal minus 2.25 times by x. So we can cancel the negatives because they're on both sides, and we're then going to have x, or the distance, is equal to 3,600 divided by 2.25. If we do all that correctly, we should get a nice round number for our final answer of 1,600 meters, which is big, but for a train stopping is not horrendous. And we're going to have to make sure that we can sort of double check our answers. There are a couple of ways of doing it. I think that's by far the easiest one, so we're going to go with that one for now. And next up is the kind of question they chuck in at the end of a whole big question where you've just spent ages doing a 6 marker and you've got a bunch of other tricky questions in here. This one is really straightforward, okay? It comes up a lot. It's all about stopping distance. So it's illegal for train drivers to drink alcohol before driving a train. Explain how it affects the stopping distance. It's 3 marks, so we've got to be specific with our language here. So what we've got to say is, talk about stopping distance. Alcohol only affects one of them. So we'd say stopping distance, we know, just a fact. It's one of those weird equations you're actually not given, you just need to know it. Stopping distance equals thinking distance plus the braking distance of a car or of a train, or something like that. Now we need to then show off our knowledge that alcohol only affects one of these. It doesn't affect braking distance, it only affects thinking distance. How it does that is it increases your reaction time. So we say drinking alcohol increases the person's reaction time. And that's 2 out of 3 marks, and the final one means that will increase the increases the thinking distance and then for also the stopping distance as well. So you've got to be able to like split up stopping distance into these two things. Look for clues in the question. How can I get 3 marks out of this question? What would the mark scheme look like to be able to get all of them here? Right, last question. You guys made it to the end. Well done. We've got a question. This is for separate science only. We've got some wire in a magnet, and usually this question is towards the end. Generators, motor effect, transformers, usually towards the end. So make sure we know these inside out, because at the end of the test you'll be quite tired. It demonstrates an effect. It says the wire moves upwards between the magnets. Therefore, there's a reader on the ammeter, it gets deflected. Now, that says the teacher moves the wire upwards, so it's not the motor effect. The motor effect means you put current through and the wire moves by itself. Because it means the ammeter has been deflected, it's generating electricity, so therefore it's the generator effect. The next question is basically explaining why that happens. Now, this mark scheme is basically the same for all questions to do with generator effect. It's obviously going to be slightly different depending on the apparatus, but make sure you learn this basics. So you say something like the wire cuts through or moves through a magnetic field, or the magnetic field. Now, the magnetic field here is between the north and south pole. Won't always be between those two, but it is here. Then there's going to be a potential difference induced across the wire, so on either side of the wire. So basically one end turns more positive, one end turns more negative, and then what happens, current is induced because, or as it is part of a complete circuit. So we should know from paper 1 knowledge, current is electrons flowing, they only flow if the whole thing's part of a circuit. Next, they reverse the direction of the magnetic field, everything else is the same. The deflection of the needle on the ammeter has to go in the opposite direction. So if originally it says it goes to positive 0.4, now it's going negative 0.4 because the north and south pole have flipped over. Lastly, we've got sound waves and what effect they have on a microphone. So this kind of question, microphones, loudspeakers, we really need to make sure we know, because like I said, at the end of the paper, but it's the same mark scheme all the time. Explain why sound waves have an effect on the electric circuit. So essentially what is happening here. So the sound waves, first of all, if you look at them going in, they cause this thing called the diaphragm, which is just sort of a outer casing, a flexible casing on the microphone. So you say sound waves cause the diaphragm, in this case, to vibrate. We should know sound waves are just vibration of air molecules. So if they're vibrating, the diaphragm is also now vibrating. Next, what happens then, the diaphragm is connected to this thing, the coil, it's all attached together. So you could say this causes the coil to also vibrate, or oscillate would be fine. You can't just say up and down, you've got to say vibrating or oscillating. What this is going to do is this induces, that word again, induces an alternating current in the circuit. The reason it's alternating current is because he's going back and forward, up and down. So it means that's going to go just like earlier. The clue is there. It goes positive, negative, positive, negative, positive, negative. They actually led you up in this question to this answer. It has to be alternating because sound waves are vibrations. This question, mark scheme, is really, really sneaky. Sometimes it depends what you talk about in each point. You can't, sometimes if you aren't specific enough, you can't get the following mark as well. But just learn this, okay? Really, really nice 3 marks. It will be the same for a sort of generator effect equation, but with alternating current instead of direct current. Right, there we go. That's paper 2. Well done for sticking through it till the end. Be really honest with your marking. You can look up the mark scheme. I'll put it in the link for this video as well, along with the examiner's report, so that you can make sure you are being as thorough as you can with revision and you can do better next time. But thanks for watching. Please check out my other videos in the links here if you want any more exam practice for GCSE Physics.